Virgo's non-detection of it, because of its blind direction, pinned that down to a region in which there were only a few dozen galaxies of the appropriate distance.
A very important factor here was the distance measurement. So even with Virgo, the error region in the sky was tens of degrees. It's way too big to search with all the telescopes we have if you have to search all the way back as far as our telescopes can see. But the gravitational wave detectors also tell us how far away it is. And we know what galaxies are a certain distance away from us. And so that's what allowed us to narrow it down to a dozen or so, which we could search for with telescopes.
Is that like triangulation of arrival time or something?
It's exactly that.
Right. Yes?
I guess I always heard that the heavy elements were produced in supernova. It wasn't until the observation of this merger that I heard that neutron star mergers are a main source of the heavy elements. Are we changing our thinking on this? Or?
Yes. So it is true that up until maybe 10 years ago or so, the favorite site to create these heavy elements was supernovae. But as our simulations of supernovae have gotten better, it's sort of become more clear that the conditions that you need to make these very heavy elements are not attained in
Is it just the very high mass end of it?
Yes, so supernovae may be able to make things maybe up to silver or so,
Okay.
but it would have to be a very special and unusual supernova to make like gold or uranium, and maybe no supernova at all can make it.
So remind me what the mass of silver is? Iron 76?
Silver is like 120, 20 or 30-ish, and then gold is around 200.
So what were the masses of the two neutron stars?
They were both about the mass of our sun, give or take. There are large uncertainties there, but roughly one of them was a bit more massive than our sun, and one of them was a bit less.
And, so where did how much of the material that went into making the heavy elements, how much of that was in each of them? I guess it's the crust of a neutron star is made of heavy nuclei?
Yeah, so what happens is as the neutron stars are spiraling in and get closer and closer, before they even merge, they exert tidal forces on each other, and that sort of rips them apart, and it rips the smaller one apart first, or the less massive one apart first, because the less massive neutron star is actually bigger, like in terms of radius. And so as it gets ripped apart, some material gets flung out into space, so the heavy elements get synthesized in this ejecta. But then also once they actually merge and form either a hypermassive neutron star or a black hole, there is still stuff that swirls around it in an accretion disk. And from this accretion disk, you can also blow off some additional material that then can be synthesized into heavy elements.
So what is that stuff that gets spun off? What was in the crust of a neutron star that it gets spun off? Is it iron to begin with, or is it just...
That is a very good question. So what is actually, from our best understanding, part of the makes up the neutron star crust is called nuclear pasta. And
nuclear pasta?
Yes, that is a scientific term. You can look it up. And basically, what happens is if you
Can you guys serve us some nuclear pasta?
That would be extremely dense.
Yeah, but you gain weight pretty quick.
I remember 6.
Right. But basically, people do these calculations of if you take matter and you just compress it and compress it and compress it, what happens is at some point it becomes energetically favorable to capture the electrons into the protons, and they become neutrons, and that's why a neutron star that's extremely dense is mostly made up of neutrons. But then you also get these weird shapes that form, and you sort of get little balls of things that are called gnocchi. Then yes, and as the density increases, they elongate and become spaghetti, and then as the density increases even more, they become flatter and become lasagna. And then you get like anti-spaghetti and anti-gnocchi. But these are, you can sort of think of them as the gnocchi are somewhat like nuclei immersed in material. But what happens is, so when the material actually expands, it goes through a phase what's called nuclear statistical equilibrium, and that's basically you can take neutrons and protons, assemble them into nuclei like iron, or disassemble them, and as the temperature drops, they will make some iron and some other somewhat massive nuclei that are much more neutron rich, and those then produce the seed for neutrons to capture on and form even heavier elements.
So how does this heavy element crust get on the neutron star in the first place?
Well, it is part of the neutron star, right?
Yeah, but the neutron star came presumably from a large supernova,
Yes,
which was the collapse of an iron core
yes,
to make neutrons.
yep.
How was there iron left over?
Presumably it was.
How did the iron get back on there, I guess?
I mean, presumably not all the iron coalesced into neutrons, right? So some of it.
It mostly does. I mean, the neutron star is essentially just this nuclear pasta that
Well,
Josh
only
was
on the outside.
describing.
On the inside, we don't really know.
In the inside, it's something equally weird, but
Or weirder.
but the iron sort of only appears after the material is thrown off. So basically, under the immense gravity of the neutron star, it's stuck in this nuclear pasta state. And once the neutron star heats up and then this material is thrown off as the stars merge, then it gets to expand. It's no longer forced to be so dense. And then it can become stuff like iron dynamically.
Yes.
And there's lots of neutrons available.
There's lots of neutrons available, that's right.
Well, how did you get protons back then?
Well, when the neutron star,
Neutrons
Jonas is
decay.
the expert, but when the neutrons, essentially when the stuff expands, it's no longer favorable to be neutrons anymore. So they become protons and electrons
Oh,
again.
okay.
And also, I mean, you get it mostly, as the heavy elements are synthesized, you get it mostly through beta decay. So you start with, say, some iron nucleus, or it's usually not really iron, it's like a very neutron-rich version of iron, but you keep capturing neutrons onto it, so you have a nucleus that has many more neutrons than it should have, and so it's unstable to beta decay, which converts a neutron to a proton inside the nucleus.
But the neutron decay time is like 10 minutes.
Yes.
Which is much longer than the time that
It's
you have.
yeah, so all the heavy elements are synthesized within about a second. Yes, and depending on exactly how quickly the material expands and how many neutrons you have to begin with, you could have, after this 1 second when the density is too low for the heavy element synthesis to continue, you could have leftover neutrons, which would then just decay on 10 to 15 minute time scale, and they could actually provide another observational signature in the ultraviolet, but that happens on the time scale of like a few hours after the merger, and it's also extremely short, so that's very, very difficult to observe.
And that was not seen?
No, because so the merger happened, and then it took, unfortunately, a few hours until LIGO was actually able to send out the alert that this thing happened, and a fairly good localization of where it happened. And so the first observations we have from ultraviolet and optical are about 11 or 12 hours after the merger. Hopefully for future events that will be a shorter gap, but it also depends a lot on where the object is and where it's observable on Earth and what telescopes are available to observe it at that time and so on.
And that's something very interesting to look for.
Yes, and actually also the very early ultraviolet emission would be able to tell us more about the gamma ray burst and whether we actually saw the burst or sort of a side effect of the burst. And because we don't have that data, there's still a debate on what exactly we saw with the gamma ray burst.
Yes.
Is there plans for more gravitational wave detectors? And if so, when are they going to come?